Jin-Si is a geographer with the USGS, Woods Hole Coastal and Marine Science Center, a drone pilot and structure for motion specialist. He supports the remote sensing coastal change group, the aerial imaging and mapping group with GIS and surveying experience. She received her BSc at UNC Wilmington. Yeah. Her MSc at the University of Victoria, and has worked with Rutgers University and the National Park Service on coastal monitoring and mapping prior to her current position with the USGS. In her spare time, she forages for mushrooms and plays a lot of wingspan. Jin-Si Over.
Thank you for the introduction. So yeah, I'm going to be talking to you about topobathy today. It's something that is pretty close to home, I guess, for what I've been doing for the past 5-ish or so years. And it's going to be 10 in the sense that I counted once, and it's probably more like 5 or 6. But we're gonna try to get through that. So this is a group effort. It is not just me I'm presenting here, but this is a work with a lot of my colleagues from the USGS Coastal Science Centers in Santa Cruz, California, St. Petersburg in Florida, and then the Woods Hole Co. And then we also use a lot of equipment and help from the Woods Hole Oceanographic Institution, which is where my center is. So this is a huge crew. We have a lot of modelers, we have a lot of field experts, and then we have a lot of data management, which is more the side that I'm on. So you just heard a beautiful intro, but basically to rehash, I'm a geologist. I'm actually a paleontologist who somehow got sucked into the beach. And it's been a great transition because tiny dead things, sand, micropaleo, it's just great all around. So I do a lot of field work now. And like I said, I'm a drone pilot, so a lot of the remote sensing stuff falls on me as well. But today we're going to talk about why do we need topobathy data. This is a Center for Coastal Mapping, so this is great. It's actually slightly relevant. I'm going to do a brief intro to structure from motion. That's what I mostly do in case anyone's not familiar with it, and some of the best practices that we're using. The state of the USGS currently for our coastal science centers, what we're doing in the mapping. I have 3 case studies for you, one from Cape Cod, one on Pea Island, North Carolina, and the last one's on North Core Banks, also in North Carolina. And then I'll finish on just a data accessibility point. Right now, the USGS's theme for the year is open science, open data. It's something we struggle as a government agency to do really well. So why do we need topobathy? I'm in the USGS natural hazards mission area. That means hurricanes, earthquakes, but mostly I deal in the coastal realm, and that mostly deals with storms. And so we have a lot of hurricanes come, and they really mess up our coast. We've seen this again and again. It's something that's going to continue to happen. And we want to know, how can we predict it? How can we forecast it? How do we measure the change that occurs as a hurricane comes towards the shore? Can we actually help the people who are about to be impacted? And one of the main ways we do this, the USGS has a total water level and coastal change forecast viewer. It takes in a lot of different science, but basically, you can go into this, you go up as a bunch of transects along the entire East Coast into the Gulf. And at each one of these transects, this is the closest one to here. This is in Kittery Point in Maine. You can look at just the National Weather Service has its tide forecast. And right below it, this is why I got the pointer. So we have our NOAA tidal forecast, and then we have the beach profile. And so this is doing just regular old, you can notice it's a straight beach slope. They have the height of the dune, and then we see where the water levels are going to go. And so you can look at the wave run-up based off dune toe, dune crest, all the wave equations for where is run-up going to happen. And when a storm comes, what they do is they forecast on here, it's going to be at your individual selected site, which one is going to be impacted on the dunes, where is the swash going to happen, where is it going to be overwashed, where is it going to be inundated. So this is for coastal managers to say, hey, here's the beach, here's what the waves and tide, predicted storms coming, where do you need to actually focus your efforts? And so what we're curious about is, well, where do we get that profile? And it's mostly coastal topobathy LiDAR. It's something that they've been collecting for years. However, on the scale that we have this LiDAR, available on Digital Coast, NOAA, thank you, but it's US Army Corps of Engineers, also US Geological Survey, inputting this. So we have these coastal LiDAR data sets, not every year, not everywhere. It's great detailed stuff, but how do we fill in the spatial and those temporal data gaps when a storm is coming, or you have a very specific site that the LiDAR resolution is only 1 meter or 2 meters, 5 meters? What do you do when you need something extremely specific? And what we've trying to done when LiDAR is too expensive, you don't have access to LiDAR, you don't have the right time for LiDAR, we've been using structure from motion, which is a modern-ish, as in roughly the 1970s, it's photogrammetry. has been around since World War I and II, but it's modern. We've basically gotten the software now to make this easily accessible for almost anyone. So what it is basically you turn imagery, 2D information, into 3D. And we're using this for digital surface models, digital elevation models at all scales, from the entire Outer Banks to maybe you want to look at this ripple on the floor. So to do structure for motion, you need good photos. You don't necessarily even need control points, ground control, but it's necessary to put it into real frame coordinates. So you take that original photo of the beach, you have a bunch of overlapping photos, chug it into software. We use Agisoft Metashape, and then you output a 3D model. And we're doing mostly models of the beach. We have dunes, bluffs, bed forms, coral reefs, mostly for change detection. That is mostly the thing we have. A 3D model before a storm, 3D model after the storm. You can look at the change. But how does it work? Honestly, it's magic. It's math. It's mostly math. But if you remember I don't know if you still have these in lab, you got the stereo glasses out, you get those big old topo things. You stare under it, you get a headache, but you can see that you have a 3D surface. So that is stereo photogrammetry. And so that's what we do. For example, if you're looking at it, you're standing still, you look at two things, the fact that your eyes are spaced apart, that's the math, and you can get 3D. Structure for motion is, I'm gonna close one eye, run around the room, but I can still see that we're in 3D. So that's what photogrammetry is taking advantage of. The fact that we have motion to get different angles so you know where the geometry of your camera normally is to get 3D elevation. So to get the imagery, this is mostly what I'm going to talk about today, is that you can use planes, drones. Honestly, we're going to talk about balloons, which is super really relevant right now. And then, but we also have the ability to just do SQUID 5. This is underwater aerial image, not aerial, it's underwater imagery where you just move on a boat, it has 5 cameras underneath it, and you get your structure for motion that way. Or just take your iPhone, go on the beach, take a bunch of overlapping photos. So coastal applications, how do we use this structure for motion to get to where we want to be? So Cape Cod, the first one I'm going to talk about, we're going to do kites, cameras, balloons, and boats. Just a quick brief intro of what we're doing. So on a small scale, this is Cape Cod. So if you're not familiar, go 2 hours south, it's the big elbow. I work on the elbow part, and then out on the outer bar, or the outer cape, is Cape Cod National Seashore. This is a collaboration with the National Park Service. And they want to know, we've done a real good job of conservation with seals. Seals are great, we're super happy. Seals bring sharks. White sharks make people extremely afraid, maybe not necessarily for good reason, but it's still a problem because we have tourists on the beach all the time. And it turns out, when you have an outer bar, in the summer, over 50% of the time, there are white sharks likely between that bar and shore. This is a statistic that scares a lot of people. And so our part of the job is not shark related, but the USGS is trying to monitor where that bar is. And also, if you add a bar, back to our total water level viewer, what happens if there's a bar? How does this affect runup? And is this something that we can incorporate into the total water level models to make any difference? Is it something we need to include? So at the Cape, we have 2 different study sites. At each one, we have a coast cam set up. These are 2 different cameras looking down. Every hour, they take about 10 minutes of video, and then we average over that time period. So we can pick up light, dark, just a snapshot of where the beach is. We calibrate it on the beach. So these are ground control points in view. We've calibrated the cameras themselves, and you can create basically a stereo image. So we can pick out where that bar is. We can pick out where the shoreline is. We have it every hour. We can basically show and correct it for tides where that bar is, if it's moving, and we have a way to basically monitor the bar. In order to also ground truth in general, because this is just looking at a small section of the beach, we're also doing a 3-part survey to basically ground truth our camera imagery. So we go out, we take some ground surveys, we have elevation points on transects along the beach. That's pretty standard, it's typical. But then we have the helicite. So the National Park Service does not allow drone use. It scares the birds. They don't want people having drones on the beach because then they think they can have drones on the beach, even though we have permits. So to get around this, we asked them, hey, can we fly a kite? And this, I'm going to attempt to play this for you. So the helicite is basically a way to get around drone use. It is helium filled. It's decently cheap. I think it's less than $2,000. And we take it onto the beach, it flies pretty nicely, and you just attach a camera to it. And so here's Peter Tchaikovsky and I filling up the helicite. And it's a gigantic marshmallow. It takes about 2 people to work with, but we actually have to go out in March, and I'm really worried someone is going to shoot it down. But this is what we're doing. We're literally just attaching a camera to it. It has a GPS duct tape to it, and we basically drag it up and down the beach, trying to get that overlapping photogrammetry. Because it is wind derived, we've found the problem is if the wind's blowing onshore, you got to walk really far out into the water. If the wind is blowing offshore, you got to walk on top of the bluffs. So having a drone would be really nice because we can't control the winds in good weather, especially on the outer Cape. And so this is what it looks like when you throw it into the software. Before the helicite, this at the bottom, we tried this to a windsurfing kite. It did not work in the sense that my God, I was blown around. I was on a windsurfing harness, and I was basically flying down the beach. But every single blue square here is an image. There's a vector showing the angle at which it was taken. So we attempted with a kite surfing kite to do like structure from motion, mixed results. The helicite is so much more stable, like 100 times better. It would be great to have used a drone yet again, like I said, however, it works. So there are alternatives if you don't have a drone or accessibility to someone who could fly one. And the last thing we did is there are ASVs. So this is, I'm sorry, I'm just going to play. But this is February, Cape Cod, we're wearing dry suits. And it's pretty fragile. It's just a little ASV. It has a single beam that puts down your fish. He's also doing this with some poles. Peter's great. And I show this because it has an excellent beam. She falls. But there it goes. Just, full send. So nearshore bathymetry is hard to collect, right? And so what we do, the helicite surveys are done at low tide, so we can get as far down the beach as possible. Bathymetry surveys are done at high tide, so we hopefully you get that overlap between the high and low, because getting coastal bathymetry is actually very difficult. Waves make it really hard. But RoboTurtle, so that's the little guy, that's the one we just sent out, is Peter Tchaikovsky's first version. It's cute. It has about an hour of very tiny single beam. Yellowfin, slightly bigger. It's much more aerodynamic. It's got about 4 hours of runtime. Still doing single beam. And they actually get us really nice results. So this is a merged topobathy. So the entire beach, this was from the helicite, and this is what the ASV was doing. So we managed to actually get a rip channel in here. But these are the types of topobathy profiles that we're getting, that we can extract profiles from to do some science. So I'm going to this is a little bit more complicated. We're going to step through it. So this is head of the meadow. This is a profile from the top of the bluff out to the outer bower. Same thing. This is Marconi. Marconi, we've gone out 2 years in a row, and then head of the meadow, we have 3 years. We'll get that 4th data set next month. And you can see that the bar does not change that much, at least here. We have a little bit, it's getting higher, it's moving in, it's getting deeper, and the beach slope is changing. So what my PI wants to test is basically, does that offshore bar change run-up? So this is just a run-up equation from, 2022. And you don't need to know all the variables other than the fact that this one does account for this offshore bar slope. And when it happens, when you use Stockton's equation, 2016, I think, is what the total water level viewer uses. It does not account for any beach slope at all. So if you do run up with a constant beach slope, you're going to get a run up of here. When you add that beach slope, that run up is a lot lower, like statistically significantly lower. So this is actually something that will impact forecasts. And the same thing, when you have it with the observed beach slopes that we actually have collected, it definitely matters still yet again. Significantly, there's a decrease in the run-up you're going to get. This makes sense. It's one of those, good, we understand this. We have the data to prove it. We maybe should actually account for bars in the offshore. And on Cape Cod, there's anywhere from 2 to 5 bars offshore. And there's certainly offshore bars along a lot of the East Coast beaches we see. Okay, coastal applications part 2. I'm going to Pea Island. This is mostly cameras, and we're talking on a slightly different scale and a slightly different temporal scale mostly. So Pea Island, this is down Outer Banks. It's south of Duck, where there's a coastal research facility. So this is a gigantic experiment that went on 2 years called DUNEX, which is the Durham Nearshore Event Experiment. A bunch of North Carolina schools, a lot of some government entities went down, and we tried to collect as much data as possible with every single sensor possible to see what happens when a storm comes through. And so, like I said, we focused on getting as much data as possible, so not yearly surveys, but we spent 2 months down there. We had a nanopod, we did topobathy. I'm going to go through a bunch of these, but know that this was meant to capture a storm event. So we brought up the helicite again. That was a lot of fun to talk to North Carolinians versus Cape Codians about what are you doing? And the answer is, sir, we're just trying to get some imagery of the beach. And getting imagery of the beach when you're looking for a storm event is actually a lot harder. Taking that thing out in 20-mile-per-hour winds didn't work. We got horrible, horrible data. You can see in some of these, it completely cut off. So yet again, downfalls of using a helicite over a drone. You really can't control as much as you'd like the area you're trying to survey. But we did get some cool information. This is when Hurricane Larry came through in September of 2021. We had a normal beach slope, and then as the storm came in, we got extreme reorganization of the beach morphology into some cusps, which is really cool. And we proved that yes, indeed, you can actually measure the change with the helicite on a roughly 10-centimeter scale. We did the same thing. We threw out robo-turtle, we threw out yellowfin, we even threw out another one, but we managed to break all 3 boats the first day. We fixed robo-turtle, so all this you'll see is from robo-turtle, but we even tried to get some multi-beam and failed miserably. But we can see during a storm event, so we had a decently stormy September and October, but the bar has basically been flatlined. We had a formation of a decent ripple field on the near shore, and we had a bunch of deposition on the near shore face. So yet again, we're just getting baseline data that our modelers need to look at the different changes of this beach during a storm event. And to supplement this, so after taking the Cape Cod camera study, we had decided to up our game, and we put them in stereo this time. And so this way, we still have that same overlap. So here's camera 1, camera 2, more overlap than the ones on Cape Cod. And so you can actually get that stereo digital elevation model. So we can see here, this is the dune. We have those cusps on the beach, and you can get some of the bathymetry out there. Not necessarily, I don't know if I trust this, but we have bathymetry possibilities. There's sea bathy, and a bunch of things you can do to get wave heights, surface currents, a bunch of toolboxes that I'm not currently familiar with. But we did this, and so we actually have that hourly storm data to see how the different things evolved in real time. And then at each beach pole, so we had a transect going from an overwash period all the way out to the outer bar. We had poles installed. And so at each of these beach poles, we had pressure sensors, line scanning LiDAR, sonar altimeters, trail cameras. And we're still measuring that water level change, that profile change, everything that's going to happen to the beach at one point. And so we were hoping, as a storm comes up, we can measure everything that happens during an overwash event. We did not get as big a storm as we'd like, but we certainly proved some things work and do not work. And offshore, so we installed ADCP sensors, ADVs, altimeters. So we're doing this, so we installed it offshore. We saw some in the wave zone. They actually broke during the waves because waves are extremely rough. But we got some good data on the offshore bar stuff. So I don't have too much to share about this. This is not my wheelhouse, but just saying, this is roughly the results that we got from our surveys. We had pretty nice change from October from September of a nice summer, like late summer profile. And then we had that big erosion, and we deposited a bunch of stuff on the near shore, and then steepened up that beach face. And our trough altimeters showed that we did accrete. So we're basically saying, yay, the data we have makes sense. And we're still currently working on processing all of the ADCP stuff. But like I said, DUNEX was a great experiment. We have a lot of different data to sort through. My last coastal application one, this is my favorite, and I saved it for last. This is the one I've been working on for about 3 years now. So this is North Core Banks, and it is mostly aerial imagery. So North Core Banks goes south of Pea Island. Now we're on the Cape Lookout National Seashore. Pamlico Sound borders to the back. And September 6th, 7th, Hurricane Dorian, this is 2019. You would think it absolutely destroyed, I think, the Bahamas and Bermuda as a Cat 5. By the time it reached the Outer Banks, it was just a Category 1. But something wild happened that doesn't necessarily happen. As it went up the coast, basically parallel to the Outer Banks, that first initial wind pushed a bunch of water up into the Sound. It timed itself perfectly with tides. And as the wind direction switched as the hurricane passed, it basically, a seiche occurred, and we basically flooded the entire backside, 4 to 6 feet above mean high water of North Core Banks. Cedar Island was swamped. These are some wild cows in Cedar Island. They modeled this. We're actually basically pushed out onto the Outer Banks. 7 survived. And there was still 1 cow out there when we were there in October. So they just basically were picked up and floated or almost drowned across the Sound. And what this ended up doing is when you push that much water up against the backside of a dune, so this is all the rack that got floated, you create all these channels. It's basically an opposite problem from overwash. So Hurricane Florence a year earlier. So this is a directionality difference. So this is overwash, outwash. And we created these gigantic channels and scours through gaps in the dune on the backside that likely Hurricane Florence had created in the first place. So overwash, outwash. You normally hear of the overwash. It happens in almost every storm. You have that wave set up on the ocean side, pushes water and sand across. So the opposite occurred during Dorian. And if you haven't heard of it, don't worry. It's not necessarily new, but it's not often preserved. That's the problem. When it comes out, immediate return to normal conditions will just completely cover it up in the next, honestly, day, weeks, to years. So this is the Gulf Coast, post-Hurricane Delta, this is Louisiana, showing that same thing happened here, but you'll never hear of it because it was gone within the next week. Return flow, where water came in, then likely just came back out. This is Hurricane Ian, so just recently out in Florida. This is probably return flow, where a beach was flooded and it had to come back out somewhere. But all these features, they're completely gone now. They've just been filled in. But what we wanted to do is we knew that Hurricane Dorian was coming. We had just gotten supplemental funding after Hurricane Florence to fly the entire coastline to do structure from motion. And we got so lucky that we flew pre-Dorian imagery, and then we flew post-Dorian imagery. And we got incredible results. I'll show you them. But basically, since then, we've flown 15 times over the entire Outer Banks. We're doing structure from motion for the entire thing. So here's just a stretch. We do 4 overlapping flights. It's roughly about 60 to 70% overlap. It's a lot of imagery, roughly 12,000 to 15,000 images per flight, each at about 20 megabytes per pixel. So we're talking about roughly 2 gigs of data per flight, just for the imagery alone. Then we make the ortho mosaic. So this is just an example cutout of the orthos from pre-Dorian, post-Dorian, and then 2 months after. And what happened is that we actually, the initial results were, holy cow, Dorian made all these channels, about 100 of them. And then almost instantaneously it got plugged up. But because they were so big, we actually had the formation of ponds. So this is the elevation model structure for motion, filled in with some LiDAR that they flew after Dorian. And here's the difference maps. So huge chunks of the island came out, about 18% of the total volume. Like this, we talked to the Park Service and he jokes that he lost a quarter of his island. It was wild, but we've done the volume stats. We think it's almost recovered completely, except for some of these ponds. So that's the story I want to tell today. So here again, here's just a larger section of North Core Banks. We have all these different channels, roughly different depths, but mostly only about 2 meters deep. Most of them have basically stabilized. But we have the ortho showing that 2 months later, almost all of the ponds, or at least the channels themselves, have been plugged. So we have that pond formation. So I have a little quick, hopefully another video. I'll walk you through what happens. So like I said, 1 year of recovery. from the pre-Dorian. So we have all these scars from Florence. So we have the gaps, so DM's on the top, orthos on the bottom. And all those gaps that were already there, as would make sense, formed into these channels. So it's taking advantage of the fact that there's already a gap in the dune. And then we have normal conditions return and we start to fill it in. So this is 1 month. 2 months later, the pond's cut off. We have a return. The berm is almost at the same height as it was pre-Dorian. So we want to, like, how often do you get another storm that's going to go over that berm? And now I think we're almost a year. So we're moving, things are moving, but the ponds themselves appear to have stabilized. So channel throats are filling, like I said, it's pretty much confirmation that things are filling in the recovery. So this is another GIF. So this is 3 years now for that pre-Florence, post-Dorian. And so that yellow line is the same, and so is the red. The yellow line happens to be this profile. So red is that pre-Dorian, ton of sediment, completely gone. And then we have the berm coming back up 2 years later, and then it's actually lowered again when it last occurred. But how is that happening? Because at some point, you have to be able to, like I said, re-breach that small part of that berm that's already been recreated. So you can see that we have vegetation's already returning. We have a completely different color. So something's happened to the pond itself. So how do we measure what's happening in these ponds? That became the next question. Who's using the ponds? This is something like resources management wants to know. Is it going to be birds? Is it fish? This is an uninhabited island. It's mostly for fishermen. So what are the raccoons doing? What are the cranes doing? Is this something that is something we should follow up on? So how are the ponds filling in themselves? So you saw that the color of that pond was kind of icky after the first. It means there's probably some tiny dead things out in the water falling, probably pretty organic rich. The winds are insane out there. So there's likely aeolian transport filling in these ponds slowly. A lot of it can be rain runoff. We actually see these channels filling into the ponds from the overwash. When those overwash events can occur, that must be what's bringing the majority of the sand into these ponds. And then you have that balance of evaporation and precipitation that's happening before it saturates the ground table. A few of these channels are attached to the sound, and so they might never fill, or at least they're going to have a lot harder time as it's tidally influenced. But we wanted to know how deep it was, so we took out, this is Yellow Cat, slightly, we're at 4 boats now, in case you're counting. So this is a little ASV, it's cute, like I said, run by a drone battery, has a little GNS receiver on it. And we drove it to do some bathymetry. This is just an example of the sonar we got. And you can see almost all of it's less than 2 meters deep. They've actually gone pretty shallow in the last 3 years. We took some sediment samples off some kayaks, so hopefully they haven't been run yet, but we're hoping to see that it's a lot of finds. And the fact that this is filling in not just from overwash, but we have other sources as well. And we're starting to do some analysis on these ponds because we have those 15 time steps. We want to see, so this is the channel area from Dorian. And then by the time it hits October, a month later, we already have ponds forming. So how is the area? So entire channel is probably gone. Those ponds are now decreasing in area. We haven't figured out the volume estimates, but at the moment, that's a huge change. We have very rapidly shrinking ponds. And any wildlife that has established itself in the past 3 years, I assume they're just going to adapt because this is the cyclic nature of these barrier islands. They're super dynamic. They're going to be rollover constantly. They're going to have ponds form, ponds are going to go. But is this something that we care about for plovers? This is the main one that my colleagues are working on, is how do these overwash events actually increase plover habitat? Or how is the different vegetation coming in going to affect anything else? So we did some drone flights there as well. So we actually have all of the multispectral imagery. So it's going to be a very interesting way to sort out how is the wildlife expanding or decreasing now that we have evidence that the ponds are not going to be there forever. Do the fishermen care? Do we care on a morphological standpoint in the evolution of these barrier islands? Is overwash versus outwash something that's going to change as we go forward? And how often is it going to go forward? So, in conclusion, all of this data, all of the topography data, all the bathymetry data, it's driving these models and forecasts we have for total water levels, barrier islands in general. The quality of the data matters. We have very different resolutions as we use aerial flights, helicite flights, drone flights. The resolutions we get are on completely different scales, but we're making sure that we have something that is comparable to LiDAR. And then acquisition of our data, we've had to been super adaptable. You saw I have 4 boats, 2 different camera systems, the helicite. We're working on it. It's an extremely diverse environment to get aerial imagery. We were even thinking of, satellites. Let's add that last part. So I'll leave you on, this is the observed stuff, using all the data we've got. They modeled it, and my goodness, if that doesn't look the same. So this is actually really exciting data. And lastly, like I said, I want to end on data accessibility. Imagery, LiDAR, it's not small. My goodness, we're talking easily gigabytes to terabytes of data. How large are these files and where do you put them? How do you download them so that they're accessible, not just for researchers, but anyone in the public or who doesn't have the bandwidth to download 200 gigabytes of data? And who is responsible for that organization? A lot of the government agencies, I think all government agencies, we have to publish, our data must be public, especially before we publish any science on them. And recently we've had to move to Amazon or any other web mapping or online services because this is where big data is going. So learning how to use the cloud has become a major hurdle actually for a lot of the people working with big data. And one of the biggest problems we're currently facing is we have a bunch of different imagery, as I just showed you. Satellite imagery, plane imagery, drone imagery, underwater imagery, stationary camera images. We're taking images every hour at 7 different beaches. You get a terabyte easily within 2 days from all of the different stations. That becomes a huge burden on all these different systems. And so one of the goals of this year is to simplify this because there should not be 10 different ways for you to get imagery that you've never heard of. Because, like I said, we have Sciencebase. That's what the USGS normally uses to publish data. Raise your hand. Do you know what Sciencebase is? 1. You see that? That is a problem. This is a major, major problem for not just the USGS, but for anyone who wants to use our data. Earth Explorer, slightly more, raise your hand if you know what Earth Explorer is. Okay, yeah, they say a few more, not everyone though. That's scary to me. But we have this data and we need to figure out how we can get it to you. And with that, I will take any questions.
We talked about the problems of wind with your loon kite.
Yeah, wind.
You kept saying the drone would be better, but in high wind, is the drone really a viable option?
Depends on what drone you're using. So this is a Mavic 600. We were flying it in it can go up to 20 mile per hour. And because it has stabilizing potential, that's truly what we need.
It can operate in winds of 20 knots or?
Yeah, it struggles, but it's a beast. It truly is. It sounds like a Hummer when it goes up. But it depends on how the limitation for drones, right, is batteries. So high winds, which means your battery's going to drain faster as it fights the wind, but you can still get that stability that you're not going to get with a balloon. Because you really just can't control that balloon, especially if you want to fly higher up. Because that angle calculation starts to get ugly. And if you fly it lower to counteract the winds, all of a sudden you need a lot more overlap. So it means more walking in horrible conditions. So it would be great if the wind would just blow down shore. But then it just doesn't matter. But I think that happened to us once.
Give a sense of for the kite that you used, what the kind of practical weight limit is of what you could lift.
In higher winds, right, you could probably lift more. Like I said, it's at 5 mile per hour winds, it's enough to keep itself alight as you walk. Like I said, we were only attaching a camera and a system to it. That's not even a pound, really. I don't actually know what the practical limits on that were, but I feel like if you hit the sweet spot, 10 to 15 mile winds, you could probably lift a decent amount. I don't know how high up you can get it, but no, I don't actually know. It'd be interesting to find out.
Just curious.
So the the washouts when stormwater drains, those fill back in because sediment gets deposited?
Yeah.
Are the ponds that are shrinking, are they shrinking because water is just dropping and your total groundwater level is dropping post-storm, or is there more overtopping that brings more sediment?
Isn't that the question? That is the question. We don't know. We have some colleagues who have put groundwater sensors out to see if that is half the problem. But yeah, for a lot of the return flow features we're seeing is that they're shallow, and yeah, most of the sediment that comes out of them is not going that far offshore. With Dorian, we're not worried, but we think that a lot of that sediment is not in reach anymore. It's not part of that, like it's not in the system anymore. It's offshore. So when you have those smaller return flow, we think they're just forming little deltas offshore. Normal wind wave action just brings them right back in. And then you have high tide, another slightly bigger events that they're filling in. With the ponds, exactly. I don't know. We don't know why this is shrinking at this rate and for what reasons. Because some of these are stable. Like, I don't know why this one's so stable. Why is this one so stable versus this one's like, this one is going down, 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 down. And it's something we'd love to, we're investigating this a little bit more because it might be groundwater related. It could just be overwash related, or there's something different with that specific pond.
So I see you use AgiSoft's Metashape a lot. And it's great software, I use it too, but it is a Russian company. And I'm guessing that the federal agency is not excited about buying new licenses. And I'm wondering if you guys have explored any alternative software like open source or anything like that.
No, it's a great question. We had that scare exactly a year ago. The crackdown happened. Fish and Wildlife can't actually use it anymore. But it turns out the different interior branches are not apparently dictated by the same person. So the USGS and I think a few others are still allowed to use it. We have a decent relationship with them in the sense that we work pretty closely with the software developers. It is not cheap. You're right in that sense. We have used Photoscan and some of the other open source. Not extremely as well, because we found that with the amount of imagery we throw at these softwares, they can't handle it. And not in a bad way, but we're aligning, like I said, 40 SFM, we're taking those 15,000 images times 15 and aligning them all together on the at this point. And we've managed to source or interface the Tallgrass HPC with AgiSoft. And that is not something we have tried with any of the other softwares. And so at this point, if we couldn't use AgiSoft at this point, it set us back quite a few years actually. Just because of we finally wrote the report that allows us to cite it for the methodology. And that has been a struggle. So yes and no, as a whole. Jenna?
So you use the balloon kite to survey it at low tide, and then you use the ASVs to do the bathymetry, I'm assuming at high. Yes. Do you have an idea of, like, on average, what's that, like, across beach overlap of where you have both data sets, and how do you narrow in on, like, how depth seamless profile?
Yeah, so it is interpolated normally, a little bit. My guess is that Peter Tchaikovsky is, I think, our bathymetry guy. Most of this is likely the helicite, and he probably chopped off the bathymetry just because that's the wavy uncertainty part. I could not tell you what that overlap is. My guess, the tidal range on Cape Cod's pretty high, so we can get, when we aim for spring tides. So we're gonna, hopefully you get a decent amount of overlap. Yes, it's gonna change, but that uncertainty, we don't think is a big problem directly at that interface. I will say we have failed miserably to get good weather days within each other. So this one is only a week apart, but we have had to do month aparts, and this is totally going to change. These things are such dynamic systems. But as for where the bar is and where the beach is, we're confident that that profile itself has not fluctuated too much.
In that overlap, like if there is overlap, you interpolate between the two?
Yes.
Do you know what kind of echo sounder, single beam echo sounder is on the turtle?
A great question. I
I'm
have,
interested what the beam.
yeah, I have the information on me somewhere. I could not tell you off. I think it's a ping DSP on yellowfin, and then it's not on RoboTurtle. It's a slightly smaller version of something, and then it's a cogger on yellowcat.
And is there any kind of motion compensation for it?
There is. He has a decent GNSS IMU on it, and he has a Mat Let's Go that I. Yeah, that's not my job, unfortunately. He gives me the data, I publish it. But yes, in the steps that I have forced Peter to write for me, he says he corrects for it, and I trust him at this point. Yeah. Yes.
So there's some really good numerical models I know that the USGS uses and others to predict overwash events.
Yes.
And they've been shown to be really good predictors of that.
Mhm.
Is your group trying to model the outwash events and then see about the recovery and understand sort of the processes that are bringing that sediment back?
Great question. And the answer is yes. Dorian basically forced our modeling group to reassess the fact that, oh wait, outwash is a thing. And I'm sorry, I don't need to do this, but I'm gonna do it. Alfredo and oh gosh, I'm a horrible person. I didn't put Alfredo in here. Yeah, Alfredo is our modeler, and so is John. Oh my gosh, the guy who does Coast. Warner. John Warner is on it. We have a team. The paper might have just come out, but we modeled Dorian
Are they
basically.
using CSTM, do you know, or are they using XBeach?
X-Beach, I think. It is definitely a work in progress. And we have a current Mendenhall postdoc working on North Core Bank specifically.
It's a complex problem.
It's extremely
But
complex.
I'm good at the overwash events, so
Yeah.
I'm just curious how well it was working on it. So, yeah, thank you.
Do we have anything? Do we go? Chat. Do we?
Are there any in the
Yeah.
chat?
No.
The stationary cameras that are doing the stereo imagery,
Mhm.
are they determining the water location, averaging of the great waves?
Yep.
Okay.
There's a minute imagery that they average it.
So does structure from motion, does that take out the need, like, do you have an accelerometer on the camera that's being lifted, or you don't even need
You
one?
don't even need it.
What?
The beautiful, like, you could technically take your iPhone right now, take a picture across here, and recreate this 3D scene. It'd be floating in space, mind you, but yeah, structure from motion. And that's actually a really cool point. We have like a GNSS and IMU on the camera we use for aerial flights, but we only use one ground control. And how we get away with that, because we talk to most people, they're like, you need 10 ground control points. And we're like, honestly, we know where the camera is. And because we are aligning everything together, so we don't align one, align the other separately, compare, we know we line everything together. That way it's locking into each other. So that tree that has never moved ever since those 15 flights, it's acting as its own ground control in that sense, in the fact that it's going to align to itself. So even if it's offset by that meter, or we actually have accuracies that are roughly 10 centimeters, which I think is crazy to me, you're still going to have it compared to each other. And so I argue with you that it's better necessarily than having,
10 centimeters relative or in the real world?
well, it is relative to each other. I think the offset is less than 5 centimeters. To real world, probably roughly 10 to 15. It's comparable to the LiDAR collection, which is what we mostly compare. And it's so cheap. It's so cheap compared to LiDAR.
Question. And one of your slides, it was with the static cameras on Cape Cod Beach, I think. There was a reference to something called Seabathy, I think.
Seabathy, yes.
Explain what that is. And
Oh gosh, I've taken, I'm never gonna find it. Seabathy is technically, if you have, I think they normally do this with drones or the cameras. If it's stationary and looking down at the beach, and if, I'm not sure if you actually need it to be like clear or not, but they're using, I think, waves and wave breaking to determine, not super accurately, but maybe within a meter, the bathymetry of the shoreline based off wave breaking. This is mostly work coming out of the FRF at Duck, and they have workshops on this, but I think it's cool. I have not tried it.
Last question. Okay, thank you very much.